I'm going to talk about matrix completion problems. So let me just kind of get into it. I want to just make sure everybody, first of all, knows what I mean by matrix completion problem. The idea is that I have a large, or usually large, data matrix. Some of that data are known and observed, and others are missing. So just think, if you like, you have some sensors collecting data. Sometimes you might have random missing entries or something like that. And one way that's been very effective in a lot of domains is to assume that there's a model underlying our data. There's some low-dimensional algebraic structure, and we're going to use that model and that idea to help fill in those missing values. And I'll kind of give you concrete examples of what I mean by this in a second, but that's the basic problem we're talking about. Kind of the textbook example that many of you have heard about is recommender systems. The idea is that an individual has some preferences over movies. Some she likes, some she doesn't like. And we imagine that there are some base profiles of preferences for romance, comedy, action, horror, etc. And her individual preferences are some linear combination of those base preference vectors. And so with that in mind, the idea is that her rating of Shrek is some linear combination of those different things. We can learn then what those coefficients A, B, C, D are for this person, and that puts her as a point in a low-dimensional subspace, the subspace spanned by those base preference vectors. Now, in a recommendation system scenario, a given person has only rated or reviewed a few of the movies in the whole system, and we want to then make predictions. What movies will an individual like next, so we can make those recommendations. And so the idea is we'd like to figure out where those people sit in that low-dimensional subspace. And the way we're going to the problem is we have incomplete data, so we don't really know their coordinates in that subspace. They're sort of floating around, and this is the matrix completion problem. It's essentially, if you knew that subspace, you would know how to impute those missing values. And so you have to do basically these things simultaneously. Impute the missing values and learn this underlying subspace. What I'm interested in this talk is taking this one step further and supposing, well, there's no reason to really force ourselves to accept a linear low-dimensional structure. It might have some nonlinear algebraic structures. Maybe the points lie in a nonlinear algebraic variety rather than a linear variety. And we want to do the same thing. We have missing data. Now we want to learn what is that nonlinear algebraic variety. So this is a joint work with a bunch of people. Daniel Pimentel is a professor at Georgia State, Laura Balzano at Michigan, Becca at UW-Madison with me, and Greg Angie, who's a postdoc with Laura at Michigan, and me. We've worked together for a number of years, and when we were young, we worked on linear subspaces, and now we're all older, and we're working on nonlinear problems. All right, so let me just kind of explain the simplest setting again. So we have a matrix. We assume that the columns of this matrix have some low-dimensional structure. So what do I mean? I mean, like, OK, again, this column here might be a point in a linear variety, or more generally, maybe it's a nonlinear variety. Okay, so the columns of our data matrix lie in one of these algebraic sets. Here is low-rank matrix completion. So this is a problem that's been very, very widely studied and is well understood now. We have this incomplete data matrix, and I'll use this subscript omega just to indicate the missingness in this data set. Omega is often used to just refer to the masking function that says where you have observed and where you haven't observed the data. So kind of the basic approach that a lot of algorithms use, and there's variants of this, but this is sort of a simple idea that I think gives everybody a sense of what's going on if you haven't seen it before. Your input is this partially observed matrix. You want to kind of complete it, so you initially fill in the missing values with zeros. Then you do a little iteration. You take the SVD of that matrix with the zero imputations, threshold that SVD, throw out the lower singular values, truncate it to get a rank R matrix, because your assumption here, another input I should have said, is that you believe these columns lie in a R-dimensional subspace. You then have, by that truncation, you get slightly better, or hopefully better, imputed missing values. You take those, you reset the original values to what they were, and you just iterate this process. So truncating the SVD to get these improved imputations of the missing entries. Many, many variants of this style of algorithm, a lot of mathematical analysis dedicated to when this kind of iteration will actually converge and correctly recover the original matrix or all the missing entries exactly and correctly. I'm not going to go into all that, but I think I just wanted to give you a sense of how people have approached this problem in the simplest form. So I also just want to mention something because I'm going to put up a sort of variation of this result later in the talk when we're talking about the nonlinear algebraic varieties. But if I'm in the situation where I have a matrix X whose columns lie in an r-dimensional subspace, and that subspace is in general position, if I observe every column in r+1 randomly chosen coordinates, and the number of columns I have in my large data matrix is sufficiently big, then exact completion is possible. And if each column is observed in fewer than r+1 components then, or elements, then completion is impossible. So basically, what all this is saying, and there are some other kind of more combinatorial characterizations of this in the work with Daniel and Nigel there, the basic idea is that you need to have at least one constraint in a column. So if I just give you r coordinates and things are r-dimensional, there's no real constraint on things. But if I give you r+1, it sort of gives you a constraint and makes this kind of completion problem possible. Now here are some pictures of different algebraic structures of point clouds in 3 dimensions. At the top, a linear variety, and down here, 2 nonlinear varieties. This is a twisted cubic, and there in the lower right is a union of 2-dimensional subspaces. These are the kinds of structures we might be interested in generalizing that idea of matrix completion to handle cases where things are having this nonlinear algebraic structure. I'll be focusing a lot on the union of subspaces model because it comes up in a number of applications, sometimes quite naturally through just the physics of the problem. And I think I'll kind of just explain that with my first encounter of a situation where I had this nonlinear algebraic structure, which is a union of subspaces. So the problem was, this is something we were doing with a bunch of people at various agencies, but they wanted to somehow map out the topology of the internet. And the way they did it is they had IP addresses coming from all over the internet and a bunch of monitors out there at various points in the internet. And the idea is if I could measure each of the computers' distance to each of the monitors, that sort of gives me a coordinate then, if you will, for a particular computer. And if you use a technique called subspace clustering, you can then figure out which computers or IP addresses cluster into different subnets of the internet. And there's a reason for that. Basically, the idea is if you're together in a subnet, then there's common ingress and egress points that basically forces these distances to lie in the same low-dimensional subspace. Now, in this work, we were actually not able to collect measurements from each IP address to every one of the monitors. The data were collected passively. The monitors were actually sitting at places like CNN.com and other popular websites. We were working with Akamai on this. And so what we really had is a situation, I kind of said that, we had a situation where it looked like this. If a particular person used their computer to visit a website, then we could learn what that distance was. But maybe you don't go to CNN, maybe you only go to Fox News or whatever. And so we had this incompleteness, and we needed to figure out a way to solve this subspace clustering problem in the face of missing data. What we did there, and this was now, I guess, 10 years ago, there wasn't really much to choose from. So what we did is we sort of said, well, this is sort of like you can think of the different low-dimensional subspaces, these different clusters as sort of like Gaussian clusters. And then you could imagine using an EM-style algorithm with low-rank Gaussian covariances. And EM is a natural way of trying to deal with missing data. It works to a degree, but it was basically a heuristic, and there was really no theoretical support for it. And ever since I worked on that, I've sort of been having this problem in the back of my mind. I'll tell you now that a little bit about some better understanding we have of this type of problem. So first of all, for those of you who aren't familiar with the idea of subspace clustering, let me tell you about one of the popular and more effective algorithmic approaches to this, and it's called sparse subspace clustering. This is due to Hassan, let's just call them Hassan and René Vidal. Now, they were looking at this problem. There's a union of subspaces. They want to cluster points. They want to know which are the red points, which are the green points, which are the blue points. And the idea is you're going to say, I want to represent a given point, like xj up there, as a linear combination of other data points, but I want that to be a sparse linear combination. With the idea is that that heuristic of forcing it to be sparse will try to encourage the selection of a linear combination of just other points in the same subspace. And so they set it up as a standard kind of L1 sparsity problem, and they did some analysis, and other people like Emmanuel Candes and so forth did a bunch of nice work mathematically on this to show that indeed this kind of sparse subspace clustering algorithm can correctly cluster these points together under certain conditions, but all under the assumption that you have full and complete data. So you're clustering without missing data. So how would you maybe tackle the problem of dealing with missing data? Well, the natural approach would be to say, well, I know what I would do if I had complete data. I know how to do matrix completion, so let me combine those things. So basically, the idea is you would take your original data, you'd fill in with zeros, you'd do some sparse subspace clustering that puts different points into different clusters. Then you try to run low-rank matrix completion, that truncated SVD algorithm I was talking about before. You get better imputations. Hopefully you go back, try to recluster then. Maybe now you'll do a better job at clustering, and just iterate this process. And again, this is something people have tried. It's kind of like, it's almost the same thing as the EM algorithm that I was describing before that we used in our work with the network topology problem. But it's a very complicated beast to analyze. And there's really nothing I know of, no easy approach to thinking about how you might analyze and say whether or not this will actually converge to the correct solution of clustering and imputation of missing data. So let me just kind of pictorially what I was describing with that little pseudocode is you start off with your raw data. It's that gray picture at the top there. The white indicates where you have missing data. Somehow you're going to say, well, maybe I can, even with the missing data, cluster. So I'll cluster into red, blue, and green. Then I'll run low-rank matrix completion to try to fill in or get good estimates of those missing values, and I'll just repeat this process. That's what I was describing graphically. What we'd like to do is just sidestep or eliminate this kind of process of breaking the problem into two things, clustering and then low-rank matrix completion, and just think about it holistically. And what I'll describe is something we call algebraic variety-based completion. So let me kind of explain this. This also goes back to some great work by René and some of his colleagues. They had this idea they called generalized PCA. So what was generalized PCA? Well, they said, look, if I have two linear varieties, two subspaces, U and V, for example, the x1, x2 plane, and then just the x3 coordinate, that's two linear subspaces. The union of them can be written as a system of quadratic equations. So U union V, if points are in the union of those two subspaces, then it's true that x1 times x3 is equal to 0, and x2, x3 is equal to 0. So you have that system of quadratic equations, and just graphically what it's saying is that the union of those subspaces is the intersection of these two sets. Okay? So I think if you just stare at that at a moment, you can see why that is so. So that's the idea. So what does it mean? Now, let's look at this. So if I said, what is the span of points taken from this union of subspaces? So I have these two subspaces in R3. What's the span of those points? Well, it's just all of R3, of course, right? So if I take the union or the convex set that contains those two subsets, it's just all of R3. So the span of those points is all of R3. Now, if we do something a little different, let's look at what I'll call the quadratic representation. So essentially, I'm looking at the tensor product of these points with themselves. I've eliminated redundant terms in those products. So it's just all the unique pairwise products I could take of the original 3 coordinates. So it's 6-dimensional. But we know something here. We know in this case that x1 times x3 is equal to 0, and x2 times x3 must also be equal to 0. So we know those 2 coordinates in this tensorized or quadratic representation are 0. And so these vectors, expanded like this, lie in a 4-dimensional subspace of R6. And so while just looking at the original data representation doesn't show me anything about this algebraic structure, this union of subspaces, looking at the quadratic representation, there's some structure that's easily revealed by just looking at the rank. So here's a picture of just 2 random 2-dimensional subspaces in R3. So what I'm going to do is the 2 subspaces are defined by 2 equations, U transpose x equals 0 and V transpose x equals 0. So the union can just be written as the product of U transpose x times V transpose x equals 0. That's what those points need to satisfy. And I can write that. Here I'm just writing them in terms of this tensor product. And the point is that nonlinear or quadratic variety here is just an inner product in the tensorized space. So by lifting up to the quadratic space, we kind of linearize the nonlinearity. Not a big deal, but it's a nice observation, and that's basically the key one that we're going to make. Yeah, Ankur.
So it seems like one of the things that you lose when you tensorize is the knowledge that when you complete the column, that it should be a rank 1 matrix, right?
Yep. Yeah, so let's revisit that question or comment or remark in a second. I'll show you how we think about solving this problem, but you're right. We are losing some of that structure, and it'll turn out that this approach that I'm taking has its limitations. In some sense, we'd love to solve this combinatorial problem of clustering and completion, but that's very messy. This is something that you give up a little bit of something, but you gain something in terms of analytical tractability. And I think when we get a little further, you'll see where this comes up. So, right, I said that. So quadratic representation. Here in this case, we have this one equation. This is equal to 0. And we're in R6, so that reduces us to a 5-dimensional subspace in that 6-dimensional quadratic representation. All right, so here's just a picture of a bunch of different sets of data points, a linear variety, 2 nonlinear varieties, just a bunch of random points. And I'm showing you the span of the original data points and the quadratic representation of those data points. So 2 and 3 in the linear case, 3 and 6, no structure at all in the random case, 3 and 5 in those 2 cases. And so what I'm trying to show you here is that at least these 3, the random points and the nonlinear varieties here, we don't see anything by just looking at the rank or the span of the original points, but something pops out. That structure is captured once we go to this lifted quadratic representation. Okay, so just kind of to take this a little further and formalize it a bit. So we have our original data points. I'll let this x chronocker or tensor 2 just denote the tensor product of x with itself. That's going to be d squared by 1 if the original vectors are d by 1, but there's just d plus 1 choose 2 unique entries in that matrix because x1 times x2 is the same as x2 times x1. So we'll imagine we just eliminate those repeated terms. So we only have d plus 1 choose 2 unique products in those vectors. Quadratic varieties have these linear representations. And what we're going to do is I'll talk about the original data matrix, which is just each column of that is one of my original data points. And I'll call this the tensorized data matrix, where I'm not taking the tensor product of the data matrix with itself, but just each column with itself. So this is the tensorization of column 1, tensorization of column 2, so on and so forth. So it has the same number of columns, just instead of d rows, it has d plus 1 choose 2 rows. And so if the columns belong to a union of k r-dimensional subspaces, so it's a particular nonlinear algebraic variety that we're interested in, then the rank of the original data matrix is the min of the dimension of the columns, or k times r. K, the number of subspaces, r, the dimension of each. And the rank of the tensorized data matrix is d plus 1 choose 2. That's the number of rows in that tensorized data matrix, or k times r plus 1 choose 2. R plus 1 choose 2 is basically the dimension of subspaces when you lift them to this quadratic representation. And I'm highlighting in red the k times r and the k times r plus 1 choose 2. We're going to assume that the dimension is large. And so really, let's just keep in mind that the min is going to be the k times r or the k times r plus 1 choose 2, because that's what we're going to kind of keep track of. And so we have, like, say we had two subspaces, two-dimensional subspaces, u1 and u2. What does this mean? Well, we're going to look at the symmetric tensor of that basis, u1 with itself, and we're going to get a three-column basis in that tensorized representation, and we have a similar symmetric tensorization of the basis u2, and that's where we get this r plus 1 choose 2, because again, there's some, we're only looking at symmetric tensors because the quadratic representation is also symmetric. Yeah?
If you use subspaces, could you express it as k-symmetric polynomials?
Yes, so you can, I'm going to focus on the quadratic case, but you can go to higher order monomial representations or tensorizations, and that will buy you something. I'll come back to that at the end, but as we've heard before, going to even a third order tensor presents more computational problems, so I kind of going to stick with the quadratic one for now, and then I'll come back to that at the end. That's a great point. Okay, so we have our original data matrix, the tensorized version. We also have the missing data versions of those. So in the missing data tensorized matrix, if I'm trying to form the product xi, xj, I can't form it if I don't have both of them. So I'll have a missing entry in the tensorized representation whenever xi or xj is missing. So if I have m observed entries per column in the original data matrix, I'll have m plus 1 choose 2 observed entries per column in the tensorized version. So this is just a picture of that. If I'm missing, if I have 2 observed values in the original matrix, then I'll have 3 in this tensorized version over there. And so everywhere where x3 would have been involved in a product, since x3 is missing in the original column, I can't form those products. I already explained this idea of the rank as how it relates to the number of subspaces and the dimension of the subspaces. And so here is the kind of intuition. So if I want, so to solve a low-rank matrix completion problem, that's the idea we're going to take. We're going to say just lift it to this quadratic representation and just try to do low-rank matrix completion there. So how would that work? So low-rank matrix completion of a rank R matrix requires at least R observations per column. I told you it was like R plus 1 before. So let's just think of R as being the key number. So if the rank of the original data matrix is k times R, and I'm observing m samples per column, then what that result is telling me is that m has to be bigger than k times R. If I look at the quadratic representation, the rank is k times R plus 1 choose 2. The number of observations per column is m plus 1 choose 2. And so if I just repeat that same line of reasoning, I'll have this requirement on m. And if I reduce that down, it's basically telling me that here in this quadratic representation, I need m only to be bigger than the square root of k times r instead of k times r. Okay? At least that's what the intuition suggests. It says I have to have a number of samples that's proportional to the rank of this matrix that I'm trying to complete. And it seems like there's some reason to hope that using this quadratic lifting will help us with that problem. It's reducing the effect of k, the number of subspaces involved. Does that make sense to everybody at an intuitive level? OK, so here is then the algorithm that this suggests. It says you have your partially observed data matrix. You tensorize it, as I described. Then you just run your favorite low-rank matrix completion on the tensorized representation. And then you can sort of pull it back to the original representation just by using the SVD. So let me show you it in pictures. I think it might be a little easier to understand. So there's the original incomplete data matrix. The gray areas are places where we're supposedly missing data. We tensorize it. We have a lot of missing gray areas now in the tensorized one, as I was explaining. We run low-rank matrix completion. Hopefully we fill things in correctly. Then for each column in that completed matrix, we're going to reshape it into a square matrix. Right? It's basically X tensor X, which I can just reform into X, X transpose. Now I have a square matrix. I use the SVD to find the principal singular vector. I stick that in. That's my completion. Does that make sense? Is that clear? Is there a question up there or just a hand? OK, good. All right, so what does this all mean? So it's saying, oh, you have a nonlinear algebraic variety. You do this tensorized business. Everything looks nice and linear. We know how to solve the linear problems. It's a familiar story that we use a lot in data science and machine learning. So is this just standard low-rank matrix completion? Is there anything interesting to say here other than this observation that maybe tensorizing linearizes things? Yes and no. So let me explain why it's a little bit more tricky. And I think that it should be kind of obvious where it's tricky. One of the key kind of tools or assumptions used in an analysis of basic low-rank matrix completion is that you have this missing at random setup. What's happening once we tensorize is there's a lot of structure in that missingness pattern. It's dictated from the original matrix. And I'll show you what that means in a second. So we had a paper where we did this. We just kind of implemented what I just described. It was sort of that heuristic and that intuition with some very encouraging experiments. But we had this kind of wrinkle about we really didn't prove that it would work because the pattern of missingness that I have over here in the quadratic representation is a deterministic function of the missingness pattern in the original. And that makes it difficult to prove anything about this. And in fact, when Rich Barrett, one of the organizers of this meeting, heard about it, he kind of blew up. He really got upset. He went on a tweet storm, and he posted this. He said, how bad can these measurements be? Don't look sufficiently random to me. Bad or sick measurements. He was really hot. He got a lot of likes on that. And it put the pressure on us. I mean, we felt it. We thought, wow, we got to do something because Rich is pissed. All right, so here's again, now I'm just going to go through with pictures what's going on and what the problem is. So we have our original data. We look at the tensor product. That's what it is. We have all these products. We look at, some of them are repeated. We take those out. And now we have this thing that I was talking about, this X tensor 2, which is just the set of unique products generated by that tensor product operation. Now, the sampling is restricted in that quadratic representation because it's just a function, deterministic function of where things were missing in the original representation. So what does that mean? So let's say that in the original domain, I had missing at random, and in each column I'd just be missing one of the entries. Okay, so I have those are the possible patterns of missingness in the original domain. And over here, that means there's only 3. There's going to be only 3 over in the quadratic representation. So in other words, you could imagine there are many different patterns of just general missingness in the matrix. There are 20 in this case. They're missing 3 out of every column. 17 of those 20 are never ones that we can generate through this tensorization process. They'll just never turn up because of this deterministic mapping in terms of where things are missing in the original and the quadratic representation. So the sampling is really restricted. It's not just a missing at random kind of setup. And so that makes it difficult to even say whether this will work or not. So what I'm going to think about is I want you to just kind of understand what I mean by this notation. So let's just say I have a large data matrix, and I can observe each column with one missing entry. And so I'm just using this omega to denote the patterns of possible observation that I'll see in the original domain. And over here, this omega tensor 2 is the pattern of observations I'll see in the quadratic representation. So how big of a problem is it that we have only a small subset of possible missing observation patterns in that tensorized thing? So that was the problem I started to ask myself. And first of all, I said, well, let's try to find a situation where it's a problem. And it wasn't very hard. This is basically the first one I looked at, and it made me a little nervous. So I said, let's consider a case where the columns of X lie in a union of two one-dimensional subspaces in R3. And then in that case, it's easy to see that the rank of both the original matrix and the tensorized data matrix is 2. And suppose we have 2 entries per column. So that means we're missing just 1 entry of each column. In this case, M is equal to 2, as I just said. That's how many observations we have per column. And that's less than the rank plus 1. The rank is 2, so the rank plus 1 is 3. And so what we know just from basic low-rank matrix completion theory is that if I'm only observing these types of observation patterns, there's no way I can uniquely determine what that underlying low-dimensional subspace is. Now, if you go over here to the quadratic representation, now we'll have 3 samples per column. It's still rank 2, so we're in the situation where the number of observations per column is equal to the rank plus 1. So based on our kind of understanding of low-rank matrix completion problems, you might say, well, maybe that's enough then, right? We meet that condition that I flashed up before. The problem is that you can see it right here. If you look at this third column, here I'm saying, imagine I get a lot of data where I'm observing on the last 3 coordinates. That's that particular sampling pattern that can come up in this situation. I could use those last 3 coordinates and many observations of those to learn the projection of that full subspace onto the last 3 coordinates. But there's not enough overlap with those and the rest of the coordinates in order to kind of link up these subspaces and uniquely determine the rank 2 subspace even in the quadratic representation. So even though we somehow seemingly are getting a little bit more in terms of measurements per column, it's still not enough to actually nail down what that subspace is. So the next thing I said was maybe that's just an artifact because it's a small, low-dimensional problem. And that's more or less what the actual truth of it is. If we go up to a slightly bigger situation, so we have 5 one-dimensional subspaces in R5, then the rank of both of the data matrices is going to be rank 5. The rank is 5, so if I'm even missing just 1 sample per column, there's no way I can solve this by low-rank matrix completion in the original domain. I'd have to do something nonlinear, like this subspace clustering idea or something. So I can't just use low-rank matrix completion there. It's clearly impossible. But if we look at the quadratic representation now, again, looking at what the sampling patterns are, it turns out that if I'm observing many observations supported on this set and a bunch of observations supported on that set, I have enough information linking these various projections of the full dimensional subspace together in order to uniquely determine the subspace. So in this case, low-rank matrix completion of the original data matrix is impossible, but low-rank matrix completion of the tensorized version can work. So here is kind of the formalization of all this. It's basically generalization, or in the spirit of what I described before for standard low-rank matrix completion. So if you assume that the n columns of the matrix lie in a nonlinear variety that's contained in a capital R dimensional subspace of the quadratic tensor space, and if each column is observed in at least square root of 2 times R plus 2 randomly selected coordinates, and the number of columns is sufficiently large, then completion is impossible. And if you're below square root of 2R coordinates, it's impossible. So basically, it's sort of saying that in general, there is something we can do in this situation, and it almost mimics what we see in the sort of standard low-rank matrix completion world. And so this, again, is kind of just a diagram of what we're doing. We have this nonlinear kind of representation of our data. We linearize it through tensorization. We do what we know how to do well, low-rank matrix completion, and just use this SVD to come back. So here are just some pictures of how this works. So in this case, we're generating different random instances of unions of subspaces. The dimension of the ambient space is 15. Each subspace is two-dimensional. The number of subspaces ranges between 1 and 20. The number of samples per column, M over D, is what you're seeing on the vertical axis, and the number of subspaces is the horizontal axis, and the number of columns per subspace is 50. And I'm comparing, just saying, let's just ignore the fact that there's nonlinear structure, try low-rank matrix completion. The EM algorithm, what I talked about before, an algorithm that uses this idea of sparse subspace clustering there, and then this low algebraic dimension matrix completion, which is the algorithm I was describing. And you can see black here is failing, white is succeeding, and so we need, as the number of subspaces increases, we need more samples per column, as we should expect, but the new algorithm that I described is working better than the others. And what's interesting here is if you look at these red dashed lines, they basically exactly are closely following what the theory predicts, that it should be like k times r growth in terms of how many samples per column you need if you just worked with the original data representation, and square root of k times r if you worked with the quadratic one. Okay? So I'm just about done, but let me kind of just now say a little bit about what are some open questions. So the sample complexity of low-rank matrix completion for linear subspaces is very well understood. We need k times r samples per column, and we're going to need k times r times d total columns in order to solve that problem. If I look at this low algebraic dimension algorithm that I was describing, where we work with the quadratic representation, then we can get away with fewer samples per column, square root of k times r. But we really don't know. I said the theorem that I presented just said if n is sufficiently large. We don't know exactly how large is sufficiently large, although experiments seem to suggest it doesn't need to be that large. But we haven't really nailed that down. Information theoretically, we actually do know, if you give yourself arbitrary time and computing power, you could solve this problem. You would only need to have about r samples per column, and you would only need about k times r times d columns. And so that is possible. There's enough information in the data if that is true, but there's no efficient algorithm that we know of recovering the matrix. Now, this is getting back to a question that was raised up there. You can extend this to p-th order tensors. And what happens if you do that is, instead of square root of k, you have the p-th root of k here. And so that's great, right? We can essentially undo that. We can get closer to what we know to be information theoretically, the limiting requirement. But once you go to those higher order tensorizations, we run into problems. There's no simple SVD-like algorithm we can use for that kind of unfolding or pullback thing. So that's another interesting area for work. Now, I'm just going to close. It'll take 2 minutes. We've heard about deep learning. And every time you think about any problem today, you should say, well, how would you do it with deep learning? And so, and some of you are probably as old as me or older. And you might remember Jack Handey deep thoughts. And I'll just give you one Jack Handey thought. So if trees could scream, we would probably, would we be so cavalier about cutting them down? We might if they screamed all the time for no good reason. I mean, that's something we should ponder tonight over drinks. But let me just say, so now let's talk about deep thoughts on matrix completion, because you have to assume if there's a problem out there, then somebody's applied deep learning. So I did a little bit of a search, and of course these are just a few papers. There's probably 20 more by now. This was a few months ago when I did this. I looked at a few of them. They look kind of interesting. Maybe there's something going on. This is the basic idea. I'll have a neural network that somehow I train. I'll put in an incomplete vector, and it'll spit out the imputed values. Okay? So here was the algorithm I described. I'll just show you that this is a neural network. So here's how it is. I have my input. I'm tensorizing it. So I have these quadratic nodes. I think, Joan Bruno was talking a little bit about polynomial networks. So this is maybe an instance of that sort of thing. So you do that. So that's the tensorization. Then you just have to do PCA. That's what low-rank matrix completion is doing. We know we can do that with an autoencoder network, just with linear nodes in the hidden layer. And then we have to do this pullback, which was the SVD, which we could implement as a power method, and that's just a recurrent neural network. So if you stack this all together, it's a neural network. So maybe. I do think that it's interesting to think about how network structures like this or like other deep networks might be useful in these matrix completion and data imputation problems. And so I'll just stop there and say thank you.